Dude is mine is not for rent. So when you got a government. All right. So what I'm really looking forward to here is, all right, one thing at a time. I need a move instruction. So we're gonna look at. Okay, so move would probably have two arguments as well. So I should probably cut it. And then we have a call queue. And call queue in x86 was used to call a label. What do we have in ARM that's like that? There we go. This seems about right. Comparison of instruction set architectures. Let's see if we actually will have a call queue here or call. Nope. Instruction sets. Operations encode length Indian NAS. No, I think this is more meta. Like comparing properties of them rather than the instruction sets themselves. What am I listening to here? Oh, Kitty Lee's solo album. Okay. Ba-dum, 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 ba-dum. I think Godbolt might be a good resource here, right? So, let's say if we open OCaml, we want to have an external that I think the function we're trying to call here is readint, right? So readint, that's a unit and brings an int back. It's going to be called readint. That's fine. And then we sort of want to call that. So how is that? Actually, let's make a function here, right? Readint. So this is. Wait, didn't we have ARM support? I thought we had ARM support. Lambda editor 1, what's all this stuff? I want to close it and hopefully you won't need it. x86, that's all we have here. All right, that's no bueno. Um, but we could do this in Rust maybe. Hopefully, the Rust stuff has an ARM target, ARM output. Where's the architecture? Can't find it. Okay, so I'm gonna have to pass in some flags for Rusty. So Rusty, target Arch 64. Cool. So dash dash target, and then we can do Arch 64. Let's say Darwin macOS. I think actually it's the other way around. macOS Darwin. All right. Unknown. Linux unknown. You know what? I shouldn't be guessing like this. There should be something here. ARM. Um, platform support. Cool. All right. So that's a little more like what we want. I don't want the square function here. I do want to call just an external function, right? So we'll do call square or actually readint, and we need to define this extern. See readint, right? Readint, and this will be unit, and it returns 932. Oh, sorry. I think it's going to complain. This should be unsafe, right? So unsafe, fine, whatever. BL. So BL is for what? Branching on labels? Is that what that stands for? So ARM instruction BL. Documentation ARM branch and link. All right, cool. Branch and link with a conditional, and then we have a W optional instruction with, and then we have a label. All right. So BL of label, that takes a label. That's good. So instead of calling call Q, we're gonna just call there call Q. This will be BL. All right, and so now this is saying when we turn read into readint and then a move, then we want to get rid of that. We want to move from that the racks register into var, or the other way around. Registers. We don't have racks register anymore. So which one is racks in ARM? x86 racks. God damn it. 86 racks ARM equivalent. What is the racks register in ARM? Okay, so load this stuff in here. Racks is R0. Cool. So if we see racks, is that the only place? Yeah, R0. Cool. And then we have add queue, which we won't have, but I think we do have add here. So an instruction add. Yeah, we do. So add queue becomes add. Neg queue probably becomes nag. We might not have nag. Let's see. x86 nag to ARM. And in the meantime, we're gonna check here. So I, and we're just gonna do -I and see if there is a, whoa, that's a bunch of stuff. Let's do, what do we have here? We have compiling. So I want to check. We're just calling add here. We got SP here. What's SP? What is all this branching? Got the whole panicking. Let's see. Rusty, no panic. Remove panic. So we're using negation here. I guess ARM64 ARM. Okay, we got ARM right there. Sounds good to me. Let's see what the instruction we get. We don't actually have that. We don't have a negation instruction. That's fine. So how do we do this here? Because we're doing a translation, right, of the sort of negation variant that we have in our C language here, C var. the backs of cars. Be cool or be cast out. Bam, 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 bam. We help to smooth the unapped track to truth, but the suburbs are chance to soothe the restless dreams of youth. I am not seeing it. So adding store register calculates an address from a base register value and immediate offset stores the word from register to memory. Can use offset, pulse index, or pre-index addressing for more information. And then we do what? So we store in the register. Let's see. We push R7. Pushes where? To the stack. Okay. And then we subtract SP. What's SP? We've seen this before. Number 12. Very confused by this. This is not what I was expecting. So we push out on the stack. We subtract from itself. We add. Okay, so SP will be a register. Let's assume that for a second. Are we adding 0 to the thing that we want here? Is that what's happening? And then we're storing the thing, R0, the results. Okay, SP instruct, no, that would be IP. And then we load, and then we do reverse subtract. Reverse subtracts immediate, So are we subtracting twice here? This is not what I thought was going to happen. All right, let me try something else. Let's say we have no arguments, right? I guess if we look at me. Int num 0, right? If we do minus num, I would have thought this would have inline the whole thing. But all right, at least we can see that we have a move of 0 into that register, which is now the variable, right? And then here it is. So this is the stuff we want. Can I see that as well when I have an argument here? Yeah, I guess I can. So we load, I guess, register 3. Let's see. Again, 0. We need a brace there. Cool. So register 3, we move 0 into it. And this could be a number like 2112. We'll see that there. Perfect. Cool. And then we do store. And we store register 3 on register 7. And it immediately, and an immediate offset starts to work from a register to memory. So what the hell is for here? I guess that would be the offset. Okay, so we're storing 2112, which is already in register 3, into register 7. But we're offsetting it by 4. Does that change if we change the number here? Go 0, 10. Yeah, yeah, okay. So this is producing different code, different instructions at least. All right. We might not need to care about this right now, but eventually. So this is how we load the thing, and then after that we're loading. Why do we store it if we're going to load immediately the value that we already have somewhere? I guess reverse subtract immediate subtracts the register value from an immediate value. View assembly documentation. Does not open the assembly docs. That's fine, but let's look it up. Destination register, register holding first operand, and the flexible second operand. I don't get that. Why are we taking 0 out of that? Oh, reverse subtract. Is this subtracting this from 0? I think that will make sense, right? Subtract the value Rn from the value of. Okay, so that's, yeah, right. Got it. I don't really understand why we need to do this whole loader and move and then store and then load the same thing we just stored before we do the RSBS. But I think right now we would mostly need the RSBS, so I'll go with that. We'll see RSBS, right? And we don't have one here, so I'll RSBS, and this will be arg for now. We'll have to figure out how to make this conditional later. And in our case, because we know the negation just takes one argument, and the second argument will have to be the literal 0, right? And then we come here, and do we say that should be int 0. Cool. And we don't have a jump, but we do have a BL, so jump becomes BL. And alright, not too bad. Line 32, we should do ARM, var program. Perfect. And then dump AST, line 71, this will be ARM var, just like this one. And this one will be ARM. So line 75, we now need to fix this one, pass assign homes. Whew. And we no longer have that, but we do have ARM var here, which will break a bunch of these things. So this will be add, this will be nag, this will be move, push, pop. We don't have a deref. Well, we need to return registers. How do we do that before? Bam, bam, bam. I think we have offset here. RBP. What was it? RBP. Hey, Adrenoke. Yeah, no worries. Like, I I have actually stopped working on Caramel some time ago. Um, yeah, I I'm not planning on working back again on it. I think if I would do a lot of something like a lot closer to what the Louis Pilfold is doing with Gleam in terms of how to approach the project. But essentially, I beat a lot more than I could chew with Caramel. It was just a much larger effort than I predicted it would be. But yeah, I would love to see a language like that on the Beam, and I think Gleam these days is pretty much that. Yeah, yeah. I think the biggest part of it is just making sure that the ecosystems are somewhat compatible. You know what I mean? Like you would need to rewrite essentially the entire standard library of OCaml, or at least reuse all the types and find a way of fitting the implementations with like Beam code. But yeah, none of the mutable stuff would work. So much of the stuff that you expect to run just wouldn't, right? The object system is something I never looked into porting either. By porting, I mean trying to understand how the hell would that work on the Erlang side. Yeah, the last rewrite of Caramel though, the one that let's see if we can open that here. The one that went, it's a branch here called Sugarcane. So it's newer. It's like February last year. Newer. It's pretty old. But this actually went a little further. There's like a new compiler, and I was working on a new syntax as well. So it wouldn't be 100% OCaml. And again, like just way too much. But this thing actually compiled down from I forget. Lambda core is the lower level representation of Camel, right? Down to core Erlang. I don't remember where that code is though, because I can't see it here. But yeah, we have this little intermediate representation B for Beam, and yeah, I don't know. I feel like this rewrite of the compiler was much nicer, but it also didn't go anywhere. Yeah. I really wanted to get a macro system in there because that's one of the things that frustrates me the most with OCamls. Like, there's no straightforward way of doing macros. I don't really like PPXs. They're cumbersome. Let's say that. Hey, Dave, I just saw your message. How's it going, man? Yeah. Mm-hmm. I don't know, man. Like English is not my first language either, so when I see that, it looks fine to me. Thorough. Uh, can you hear the music or not? I hope not because it's I'm listening to Metallica right now, and I don't want to get banned. Oh, you can see the chat up here. That's cool. Nice. Yeah. I also got a green screen from a friend that's moving to Barcelona, and he was getting rid of a bunch of stuff. So I got it from him, which is great. That's why you can now see the background here. Yeah, I'm from Argentina. Thanks. Oh, very nice Portuguese here. All right, I thought you said my Portuguese was nice. That's something like I can speak well enough so that Brazilian people sometimes ask me what accent do I have, like which area I'm from. The thing is funny because I don't think it's that good. No, but I've been learning Portuguese for maybe like 3 4 years, and I've been to Brazil a couple of times for several months to learn it more and practice it. So it's going further from Portuñol more into Portuguese, but well, of course there's still a lot of Portuñol in there. All right, what the hell is this RBP register? X86 RBP register. Frame pointer. Okay, so that's a frame pointer. What would be the equivalent to the frame pointer in ARM? Do we have that? I think we have our R11 FP. I think that's it. Frame pointer ARM. FP. Yeah, 11 FP. Okay, cool. So we're just going to continue with that. And this will be, I guess it's the other way around. Here we have R11. Nope. R11. My autocomplete is not doing the thing I want it to do. So we got an offset from a register there to what is supposedly an argument. What's an argument? An int? Okay, yeah, I can do an int here. Cool. And sorry, not arg int. There you go. And line 8, what happened here? Line 8. Got a var. We do have a var here. That should be fine. This variant expression expected to have type load. There's no constructor var within type load. What? Oh. My bad. So this shouldn't be a register like that. This should just be a register. Okay, so I guess this is confusing the two. Oh well, we're gonna have to annotate that and say you're gonna return an argument. Cool. That does the trick. Muito obrigado, Adrian. Alright, sub Q, we don't have that anymore. Actually, Q like that goes away. And just like we have add, we will have sub here, right? Cool. Save. Nag nag. What do you mean? All right, there is no nag. Is fudge. I guess we're gonna have to redo that thing. Oh, we don't really have that anymore at this stage, do we? And we have push of two things. Does push really take two things in arm? Arm push. That's not gonna be okay. Maybe it is. I think it just takes one. Yeah, a register list. Cool. And pop takes one as well. All right, we're getting closer to the end of the line. Here we're just gonna say arm var. What am I doing? Go back. '81. Cool. So now we need to fix the types and patch instructions. Again, we will have arm here. That's the one that's open. But everywhere else where we have x86 var, that will be arm var. Oof. Okay, so here we'll have to change all the queues, right? Just get rid of them. There'll be a couple of things that we no longer have, like we don't have negation anymore, right? We don't have deref anymore. We have offsets, right? So instead of is deref, we can just ask is offset, right? And we can do the same thing with our ref there. We can say offset. Cool. And all right, line 8 move. Why don't you like this move? Because our move goes the other way around, and there is no racks. It's R0, I think. I forget what the hell I have it here. Select instructions. Move. Yeah, R0. So racks is gonna be R0. Cool. Oh, I really don't want to flip all this stuff. Wait. Do we need to do this here? is too different. Mm-hmm. Cool. We just need to make them the same. Aren't they the same? Oh. And that makes more sense. Because this expects an argument, but the arguments are different. Because one of them will not take a bar. Cool. So offset, and then we'll do patch offset. Oh, I think I can do the same. Just patch arg. Rec. So we don't have that. We have break and branch and load for label, right? I think we actually have the same instruction set across both. Huh. Rect. Return. So what's the return here? Let's have a look. I don't know if you would help. All right, let's just have a look at that. x86 recute to ARM. Equivalent. I think we can see in Godbold as well. When we did that, the return itself. Where are you, return? So if we do just return, like so, we're loading into R7. No, from R7. Because we've moved R7 to SP. Right, so this is the stack pointer, this is the offset, and then we do branch and exchange. Oof. So we don't have a return. What's all our ARM registers? LR. Link register. All right, so that's where we jump back. So, what did we say? We needed LR. So we need Branch and exchange. Causes a branch to an address instruction. What's the difference between BX and BL? Oh well. There's no jump. Oof. I actually think I'm just gonna make this equal because the instruction set is the same in both, at least so far. So arm like that. Dun, dun. So pass, assign homes. No, I can't do that. Fuck, because I actually need to redefine argument. So either I parameterize that and use the same instruction set, or I keep duplicates, which means I need to actually extend this list right here. Okay, so let's do eval pam. Cool. My LSP is definitely not working here. LSP status. Start. Nothing. Zero. Silch. Nada. Alright. We have a bunch of instructions we don't care about right now. Most of this over here. Don't care with that one. I think LDR, we are not actually using that. Are we? I think we are. So if I remove that, something else should fail. Alright, so LDR, and we have an arg, and this will be LDR, and then patch arg. What? Tab load. Oh yeah, we do. Okay. Patch load. Cool. I am not happy with the LSP not working sometimes. Why aren't you working? God damn it. This isn't gonna change a thing. So, LSP info. Tell me. 0. What the hell? I literally just installed it again. Press Q. All right, LSP install. OCaml LSP. So I'm just gonna do a pom install OCaml LSP. Probably not call that OCaml language server. I forget what the name of this thing is. Search. All right, let's do an update here. Could it be slower? Bring me it louder. For the love of God, please. Why are you so slow? Why? It's so painful. What was the magic thing? Network health. Something like that. No, that's not it. Okay, I think this is gonna be the one. Just agree, go away. Microphone seems a little louder all of a sudden. Network quality. Yeah, it was something like that. Network quality. I think my internet should be okay. Maybe not. Maybe it's crap. Yeah. No. What the hell? Close. Go away. Alright, so now that we have that, we can install the LSP server. It's already installed. Oh my god. Why? Why are you doing this to me? What have I done to you, Obama? Are you not finding the thing? Oh, Shit, I forgot to check. We had an open PR for 30. And nope, no comments yet. What about the issue? Also nothing. Alright. It's okay. Cool. You're done installing things? Great. Thank you. Thank you so much. Just get out of my way now. Go away. Cool. What I want to do is just load this file, right? And I would like the LSP to be started. 0 clients attached to this buffer. Why? So you're installing the thing. Yeah, okay, I'm good with that. So I would expect now if I do LSP info, but I don't have anything attached. Why? Okay, maybe it's this. We have an error somewhere, line 50. So in it then, right, line 50. What does it say? It says near double equals. So there's a double equal somewhere. And of course, this is not a double equal. This is a merge conflict, isn't it? This looks so much like one. Yes! God damn it. Alright, that was the problem. Gone. So now we have that. And I think I should be able to just, you know, to A, like, you know, AB, and move them over. But you don't like it because the arguments are different. That's right. We can do patch arg. Patch arg. Oh, that's not what I wanted. Patch arg. Cool. What are we missing here? Let's do Dune sec bin dump.txt x watch. We're missing RSBS and STRs for storing. Right, so RSBS has an arg XY. And now we're missing store. And this has a single one, I think. Not two. Excellent. All right, dump AST. We go line 87 here. That's fine. We get an AST back. This is Nox. This would be ARM. And this will be ARM here. And there. I'm sorry. What don't you like? I guess you don't like this thing here. there is no push Q. So the main will have to be different. How do we do that? I guess we need to boot the main somehow. We want to do int main, right? And then we call square. We want to branch out to our function, call start. Nope. I don't know what that is. Ooh, so much stuff I have no idea about. RBP is the base pointer for the frame. So this really should be RBP, R11, frame pointer, right? RSP, what was RSP? Do we need this prelude here? I don't know. Because we needed that for x86, right? Yeah, we get this main thing. We jump to L2. At the end, we just leave and return. But we don't really have that over there. All right, so you know what? I'm gonna go away. I'm just gonna. This is probably gonna seg fault if it doesn't work though. Okay, let's see. Arch, arm. We have some offsets here to SP loader R7. I don't understand where are we doing the thing we were doing here. Oof. I forget. Okay, you know what? I'm just gonna do the east thing for now, and we'll deal with that later. Cool. So that's the program, and it should blow up, I imagine. And we're definitely not printing it correctly. So we're gonna go into ARM, and we'll do the pretty printing. Confused. Why are you not printing anything? Sweet home. Okay, yeah, that's because we're not really doing anything with it. That makes sense. So instruction, I'm gonna matching you, destruct here, perfect. Oh my god, so many instructions. We didn't really need all of them, did we? I think we can remove the ones that we're not using, and that will be most of the ones that don't have any arguments. Cool, yeah, that seems alright. So destruct, much more manageable. So we get X, Y. What is this? ADR. So we want to do format, fprintf format, and we'll do ADR, and then we want to compose the PPR, and then for X, and PPR for Y. And we can probably just start with that. XY, this will be a label, that'll be a label, loader will be a load, move, we have an argument here, and an argument there, XY, 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 Y, X. Cool. So most of the stuff should be there. What's your problem? 91. Oh, there you go. Cool. So when we got labels, we're actually just going to do pp label. And that will be the label. Cool. So now this is add. This is going to be L, BX, LDR, mov, and then we go pop, push, RSPS, store, and subtract. Cool. So now we just need to add a pp label. Forget label. This is just a string, I think. Format f printf f L. Cool. pp label like that. Cool. 988. What do we have here? Same thing. Loader. Well, we need a pp load. L. Cool. And then we'll do the same thing as this thing. But instead of label, it will be load, right? And I think here we will need to do a match on load. So destruct on that thing. Yep. Okay. So what's the syntax here? We saw the syntax somewhere here. Oh, great. I could have used this a moment ago. Immediate, register, offset. Yeah, okay, so the three addressing modes: offset, pre-index, prefix, postfix, pre-index, post. There you go, that's the stuff. So when we got an offset, right, we will have an argument, and we'll have an argument in both. Okay, so format, printf, format, and this will be bracket, right, and an argument, and then we'll do argument there. So ppr, x, ppr, y. Cool. And for the time being, we'll just do the same thing for, no, god damn it. For all of them. But I think they're not arcs, all of them. Okay, they are. What are you complaining about? You get two of those. What is beeping? Something is beeping. Alright, something's beeping, I just don't know what it is. So the pre-index mode, prefix, this one, will have that. And the post-index mode will actually be more like that. Is that what I'm reading? something's a little off here because I see an example of the load into register instruction, right? And I am missing a part because I see three things here. So I think that the first one, right, the first thing might actually be the one that goes here on the left. I just don't understand if there's something missing with this instruction instead, right? So if you go into ARM here, we search for type load. Oh. Line 84, why are you complaining? We have some other stuff here that we don't care about. Is that the problem? Look at that. That was the problem. R11FP, where are you? Line 7 from assign homes. Don't we have that? We do. That's a register, and offset takes a register and an argument. So that's fine. Oh, what? When did I remove that? 63. So this looks wrong to me, especially since we don't have a conclusion. So the program we're trying to run, right, it's sort of this thing here. We declare a variable a with value 42, and then we declare b, right, to be equals to a, and then we return a. Like that's the last expression we have in our let. So this ends up into the different like passes in this compiler, right? The first one, we lower this down so that, what do? It's been a days and I already forgot what the difference between this over here and this one over here is. But I think that we're changing the value, the type of values that things have. So we have a way of distinguishing between all the atoms and all the variables. No, that doesn't sound right. And then from there on, we are turning this into a sequence of things. And I think that this one, let's actually bring up the, I'm just guessing here, shouldn't do that. Cool. So first AST is that one over there. We uniqueify. So we're actually essentially assigning unique names to every variable that we find. So, A1. But we already have that. Or actually, no, that's fine. That's the first pass we do. So the first pass we print out, that should be this one over here. And then after that, we are removing complex operands, which I guess in this case would make it the same. But if we had a more complex expression here, right, like we were negating a variable, so if we did something like neg var, I guess we need to do a prim here, primitive. Perfect. So on the first pass, we see the variable negated. It's a primitive call that's assigning to B2, right? And in the second pass, or rather, So we make it unique, and we print that out, and then we remove complex operands, and that does not remove that. I thought it would. Maybe that's not the kind of thing that we need to. So if I do add, then we need to do this twice. All right, now I think I believe you. We have A1, F. Is this even doing the thing it was doing before? I don't think so. So what I'm expecting here is to see this expression broken up into several assignments, right? So there will be more than just let b equals this thing, right? But maybe the problem is that it actually needs to be more complex than that. Right, so this is what I'm looking for. These temporary variables here, temp1. Where are you? There you go. So this is, first negating a, and then it just returns, right? At the addition of var a with the negation of var a, and that's what b2 becomes, and then we just return b2. Okay, so that step is working. Just confusing at first to maybe needs more complexity than I thought before it kicks in. So uniquify is working. Remove complex operands is somewhat working as well. Next up, we have explicate control. And this is the thing that takes us from our little C language here, right? Where you essentially have statements, right? Where you assign. And this is called C language or C var based on the book, right? This book that I'm following. Essentials of Compilation. It doesn't have to be called that, but essentially allows us to do single assignment form, SSA. What the hell did SSA stand for? Static single assignment. Yeah. So essentially, you use a variable once, you assign it something, that's it. And that's sort of why we also have the prior pass, where we assign everything a unique name. So this will be the third, right? The third print. So first print is just unified. Second print is removing complex operands. The third one should be explicating control. So we have first one over here, right? And then we have the second one, and then we have this one where we turn everything into these assignments. Cool. Now in the next one, we actually go from this C sort of SSA language into our first assembly, I think. Yeah, ARM bar. Cool. And we're just doing an intermediate step here where we don't really go into ARM assembly, but we do ARM assembly with variables, which is not really a thing, right? In assembly, you don't really have variables, you have registers. But again, I'm following the book, and they suggest you do this so that you can operate a little closer to the assembly and do some more passes here before you actually do the register allocation, which is the next chapter of the book that I haven't started yet, third one. Yeah. I'm really liking the book. It has a lot of this exercise left for the reader, which is kind of annoying because I would like to speed run through it, right? To really get an overview of okay, this is how all the parts are connected, right? And then I can go back and dig deeper into the things that I find interesting. Whereas this is sort of forcing me to do things more slowly, which is not bad. It's just not my learning style. That's all. All right, so in this select instructions pass, we're actually converting from that CVAR language into, if you see here, handle statement, this returns on the instruction list. So if you have an atom of int1, we're just saying, okay, we're going to move that atom, right, that integer in this case, into a specific variable. Later on, we'll turn those variables into registers once we allocate homes for them. So here below, we should see, okay, move integer 42 into variable a1 like we just did before. Let, a equals int 42. Next pass, so at this point we already have this last thing here where the last thing in the program is allocated to the rax variable, which is not really a register yet. It's just like a dummy variable name we replace later. And the last thing that happens, the last instruction is a BL to conclusion. And that's the one thing we're going to change here. So instead of doing a jump to that, we're actually going to do a jump to how was it? Was it BLFP? Fuck. We had that somewhere here. BX. So ARM, BX, LR. That's the one. BX, LR. And I think LR is actually a registry. So in ARM. Okay, so it's a label here. But maybe we can do that with a register. It's also the fact of, like, the question of how tight to make this type representation, right? Nope, that's not what I wanted, or it doesn't look like the thing I want. Maybe it is though. So let's see. BX. Nope. Can't pattern match on anything there. However, here we should find it. There we go. An RM is a register. Okay, so that has to be a register. I want to put a register there. Done. Cool. So now that we have a register there, then the printer is going to complain. That's fine. We don't want to do that. We want to do pp-reg. And when we do patch instructions, here we'll do patch register. And that should also be a register. So reg. I guess we don't really need to patch registers there, so we can remove that. Cool. We're still game. So now we just need to go back here and just do R what? Let's do ARM R14. There we go. Cool. So now we should be returning the last thing at the end. Now this var rax, I don't think we need that really, but I think we will have to find the return point, the return register. I think it will be 0, but I don't know. Somewhere in here we had a list of registers, I think. Return. Maybe here. Return. Rax. So what will be rax here? I guess it's R0, EX. So this will be R0. Cool. And that makes sense there. Wait, did this get shorter? Yeah, it did. Okay. So I guess we need to change that. That's fine. If I search for rax, then we should find a couple of places. Rax, this will be R0. Oh yeah, all right, we had it there already. Cool. And then, cool. All right, that should be a little better, a little closer. So trying to understand this, right? From this pass, go back there. Yeah. From this pass to this pass over here, we're going from the dialect of ARM that supports variables, right, to one that actually has offsets into the stack. So that will be the first variable, right, A1, and this will be the second variable. And this moves 42 to the first variable in the stack, and then we move that variable from the first to the second, which is essentially this line over here, A moved into B, right? And then we move B into the return variable. But I guess all right, so we replace this var R0 later when we patch instructions. So we end up with break 0 in both cases. What? Why do we have that twice? That looks wrong. Okay. So far, this does look like, what we wanted to do. But I don't have a good measure of whether it's the right way of doing it. And what do we do next? Right, the next thing we do is to make sure that none of the instructions have more than one sort of pointer or offset. So if you look at here, the first one is an offset of an offset, and that gets turned into 2. Yeah. So instead of moving this from this offset to there on that offset, we first move it into R0, and then we move R0 into the second one. And then we do the next thing, which is what we had. And I guess that's why it's duplicated. Okay. Is that all? All right. Let's see if we can actually compile this thing and make it like at least debug it and see that we're going through the motions. Well, why is this R14? That should not be R14. That should be LR. Okay, so here, right, we have FB, IP, sorry. SB, LR, PC. Cool. All right, that makes more sense. Slightly closer to the thing that we want, I think. And I think we also have a Rocket C there. Oops. So we need to go to Rocket C and change this. This should be ARM. Cool. And now we have our little assembly file here, right? So we're going to do clang on that. No, clang. There you go. S. Yeah, that does not look good. Unexpected token in list argument. Move 42. So how do we do that in C, right? If we just want to return this thing, 42. Okay, so the register should go on the left. That's all right. Let's see, move x, y, x, y. So y is the first argument here. This shit's inverted. But I'm not sure this would make sense. How do we move? Oh, move and negate. That's a good instruction. Hmm. How to move into the second or first position in the stack? Cool. Okay. Because this is kind of what I want to do, right? Like I am working with the assumption that by knowing the variable I'm working with, I can get an offset into the stack pointer, frame pointer. But we have push and pop for that. I wonder if all this stuff is worth doing right now. Because I don't want to learn this stuff right now. I want to learn the other stages in between, right? Because there's clearly more passes that this book will be implemented, right? Implementing. And the only thing I have to compare with right now is x86. But I had some weird issues when debugging, right? Like, for example, if I just stash the whole thing, right? I think I can do the same thing here. Probably can get rid of load here. Oh, he was missing this stuff. What? Really? else did I change here? No, this is all the changes. Was this not working before? I think it was. I don't think I have anything else pushed there. Cool. Do an exec. Oh, right. I am in the wrong architecture. This is why I thought it was annoying. Okay, so now I am in 386, which means if I go clank here on test ASM, then this should build. I forget exactly what I was calling clang with. I still have to call, or I'd like to call Dune from here, right? Where I am on ARM. But then I'm spitting out at x86, and now I have to remember that. Just, I don't like it. What did I mess up now? Right, we have a main reference from implicit entry start for main executable. Clang x86-64. God damn it, 64. Main undefined symbol. macOS M1. All right, let's see. We might actually fix the cross compilation and just be done with that. Do I need to tell? Maybe I need to tell Clang, right, that I want to build for. No, Clang is clearly getting that I am on x86 and I want to build for that, right? Let's do verbose. What do you have for us? x86 Apple Darwin, good. Clang, CC1, okay, it's a version. We get some of the include paths there, I guess. And then we try to link. And we pass the right architecture. So I guess there's nothing else that I need to configure here. But maybe I am missing something. Yeah, so this is similar to the error I'm having. Link errors. Can I not link an x86 binary from ARM? Is that how it works? Main reference from implicit entry start for main x86-64 clank. All right, let's see. Don't we have that? I mean, yeah. Oh, fudge. I think, if I'm not mistaken, I had tried actually setting main first. No, I was looking at some other compilation output before last time I tried this. Yeah, something else was missing here. Where the hell did I see that? Mac. Damn, I forget where I was looking for this. Or maybe it was the main needs to be main. No, wasn't that. Crap. I should have committed that change. Don't know what I did with it. Rust. Yeah, we don't see any of that here. Let's see. So x86, 64, Darwin, Apple Darwin. Doesn't look like the thing I had before. Crap. Nope. Camera died. connected. We're back. For the time being, at least. I forget. I remember that I had changed something in the output assembly, and that had made the compiler like whatever I had written, right? What I don't remember is what, but I do remember that I saw it somewhere, probably in Godbolt, but just don't know exactly where. Which sucks because I it was something like dot global, um, so x86. Section data, section start. Oh, that was that? Didn't complain. Okay, cool. Yeah. So the issue I had, and the reason I thought, all right, I'm gonna start looking into just spitting out um, ARM instead, was that after doing that, that very tiny bit of assembly it spits out this 17 kilobyte test file, right? Even if I remove all of the global symbols, I thought the dash G was for debug symbols. Dash G. Yeah, source level debug information, right? Even without that, it just seems way too big. 17 kilobytes for that. I mean, this thing does nothing. You cannot even like print out or see the return value of it. You have to run LLDB, for example. And I also forget exactly how to use LLDB for this because I was looking into that before I went on vacation. Was this the thing I was looking at? Maybe process launch, double entry, but hopefully this has yeah, this has memory. Good. I think I might need to do load. Where are you? Process launch. No, that's old. Target create. There you go. That's what I want. And now I can do process launch, top at entry. But you see, when I started going through this stuff, I could not find the assembly that I had, nor any form of it. It just seemed like, I don't know, it could be that the assembly I'm feeding Clang is just very broken, so broken that this is really the output it generates. Hard to tell, for me at least. Yeah, I'll just for reference, right? Like there isn't any of it. It's just where is all the stuff? I have no ants. I have a couple. I have no mov queue move instructions, right? So if I just go through them, eventually we get to this jump, which I think would be the same jump as the one we have here, right? Jump start. But then it doesn't really go there. It goes wherever else. And then we have a couple of calls to some debug stuff. I forget, but I think I remember seeing something about Rosetta in here as well. At some point. I don't remember. Yeah, and then at some point I tried to also put breakpoints here. We're going to diagnostics. Don't really like I didn't expect any of this stuff to be here, to be honest. Yay. A little Gleam project I was trying out. Open folder. I think I can do code here, right? Cool. Don't show this again. No affinity assigned. Sure, restart. All right. So what we wanted to do was to grab this thing, and I think the extension is wrong. Should be S. Ooh, it's a lot of installs. Tons of stuff to use here. Okay, anyways. So I have that, right? And now I would love to just debug this thing. Running debug will not let me because I probably need to have a launch JSON file, which I don't. And let's see. If I open LLDB, can I actually run this thing with LLDB? Open and integrate with the terminal, share. So let's see. This is what I want. I want the manual, launch a new process, attaching to an existing process. Let's see, launch a new process. Cool. Can you give me a recipe? Path of the executable, arguments. Debugger commands. Right, let's see. VS Code debug assembly. All right. Does this work on Mac though? Yum Ext. Maybe it does not. Okay. Damn, already stopped. No. Okay, this rings a bell. Because when I was running that executable here, we get a seg fault, right? There you go. But I wanted to debug that. And that's how I got into this whole LDB stuff where I don't know where this code is coming from. And I don't know how to jump straight into my code to debug that. But this looks more like it. We have symbol start, we have a conclusion here, right? Now this is complaining, it says bad access 0228 on the address 0228. We're trying to subtract RBP. Is that RBP not good? Should this be the other way around? God damn it, the camera keeps turning off. Right, but this definitely looks a lot more like the assembly I emitted, right? Where are you? Here. Um, yeah, there you go. I want to put you down here. Can we do that? Hello. There you go. Cool. So sub Q, sub Q, sub Q, four sub Qs in a row, right? The first one is 42, and then RBP minus 8. Should that be 8 instead? Is that the problem? Let's start again. And I need to recompile. Cool. Clang. Where are you, Clang? Oh. Cool. Debug. We were just debugging now. Debug. No, that still complains. Why? Why does that not work? Is it because of the 42? Is it the RBB that's wrong? If I look into the book, no, that's exactly what it says here. It says MovQ. MovQ. Why do I have subQ? What did I change? Ay, ay, ay. Come on, Leandro. Alright, but this I can do here. Patch instructions. Select. Where do we do MovQ? SubQ. Never. We never use SubQ? You see in the printer? SubQ. Mother of. Alright. Cool. Right, so the first thing was that we need to print out format of printf, right? Format, and we'll do global main. Cool, that's compiled. So now this should be MovQ, whereas before it was subQ, right? And then maybe if we debug again, it would not instantly crash. I don't know what it did. I'm sorry, what are you doing? Are you even doing things? Console and command prefix. Oh, that's great. 42 is our number. Woo! Okay, so that was a problem. See, computers are easy. Oh, God. I am so frustrated at this right now, but it's just brilliant. All right, just to be sure, I'm going to try a different number, a larger number. Debug that. And hopefully this says the code is 64. I think it's because we have a U8, maybe. If I do 7, what do we get? Yeah, 7. Cool. All right. So that worked. That's kind of encouraging, but also anticlimactic, right? Oh, climactic. I don't know. So we had a wrongly printed instruction, which makes sense because we're trying to subq subtract from this value. We had a subqueue there before, but that didn't make any sense. And now we have the global main, so we don't have the linker problem anymore. Small wins. I'll take them. So let me just remove all the test stuff. Fix x86 print bugs. Cool. All right. I think that means I can actually go on to the third chapter called Register Allocations. I'm going to try to turn the camera on one more time. Boom. That worked. All right, so we go to the next thing. I don't know if you can see anything there. It's probably out of focus, but register allocation. Chapter 2, we learn how to compile the LVAR language to x86, storing variables on the procedure call stack. CPU may require tens of 100 cycles to access the allocation of the stack, whereas accessing a register takes only a single cycle. Okay, right. So that was the thing we were trying to do that was confusing in ARM, where we would use push and pop instead of these offsets into RBP, right? I guess in this chapter we're gonna go back to the assign homes pass. Cool. So we're gonna be building a graph, right, to check which variables overlap with each other or interfere with each other. And we can then do register allocation as a graph coloring problem. If we ran out of registers despite this effort, we place the remaining variables on the stack. Similarly to how we handled variables in chapter 2, it is common to use the verb spell for assigning a variable to a stack location. More sophisticated approach is to assign a variable to one or more locations in different regions of the program. For example, if a variable is used many times in short sequence and then used again only after many other instructions, it could be more efficient to assign the variable to a register during the initial sequence and then move it to the stack for the rest of its lifetime. And he has some references to Cooper and Torkson. I think I'm butchering that last name, Torkthon. For more info with that approach. Okay. What's interesting is that we'll be building a graph out of this stuff and then, using, treating the whole problem as a graph coloring problem. So something else that the coloring or the graph coloring will have to take care of is respecting which registers are meant to be sort of handled or prepared or just preserved, right? By the caller or the callee. Apparently, there's a like a disjoint set of registers. Some are for the caller to take care of. Like I want to call another function, so I'm a caller, so I need to do some things, right? Like free those registers, make sure my variables, that the values that I need to work with, are not there. And there are some others that seem to be the responsibility of the callee, the one that's being called, right? To preserve in some way, like RSP, RBP, RBX. So I guess if something is in RSP, right? I wonder how we would know that. Like, do we just by default move that value into the stack, do stuff with the registers, and then push the value back? Do we even need RSP? I guess since that one has a name, it may not be general purpose, maybe a specific register for a couple of things. So if we need to use it, then we would know. All right, whatever value we have there, we'll move around, save, work, with that register, and then by the end, put it back. Yeah. Okay. So, right, essentially, the caller should assume that all caller save registers get overridden with arbitrary values by the callee. So if I call any of the registers that I'm supposed to clean up, I will assume they have garbage. So I need to put my values back in there. And you can always assume that those are free for you to put stuff in there. And the callee ones, like the ones that you own, the registers you're responsible for, I need to be able to assume that they have the value I put there when I called you. Which means, as I assumed earlier, that if you want to use those, you will have to push those values into the stack in the prelude of the function, so you can restore them by the end. Interesting. This also starts to remind me of some of the Beam bytecode that I've seen before. It's like when I was building Caramel, I had to deal with some of these things, not directly because I was not writing the Beam sort of bytecode instructions by hand. I was translating to core Erlang, right? And then the Erlang compiler did that. But I did get to see and read a lot of that bytecode to understand what the hell was happening, right? And a lot of the register and stack manipulations were not entirely clear to me. But this makes some sense at least. The rocking world go around. Something that still trips me is the difference. Like sometimes they refer to the stack as stack, right? And sometimes they use the word frame. And I know that is you know, or maybe not. I am assuming that they're kind of the same, like stack frame, right? But yeah. Like here they say, like the convention is to use space on the frame of the caller for the rest of the arguments, right? Instead of saying to put them on the stack of the caller, right? Which is the way the phrasing they've used before, right? Quoting, this can be accomplished by saving the value to the stack, right? Yeah, anyways, in chapter 7, we instead pass a tuple. Okay, and racks is used for return values. Cool. Considering the LR program presented in figure 3.2, which is over here. Right, and they have a program where we're reading two values, right, one after the other, save them into two variables, and then we add everything together. What? Now you have the global. What the hell? You didn't have that here before. Global bean. Am I missing that from somewhere? Maybe I did miss it, and it's already in the book, but otherwise I think it could be somewhere I read them. Most likely I missed it. And I can't find it. All right. No, here it is. I definitely missed it. Yep. Cool. All right. Going back to the text. We refer to our variable that is in use during a function call as a call dash live variable. The program makes two calls to read. The variable x is called live because it is in use during the second call to read, right? We must ensure that the value in x does not get overwritten during the call to read. One of his approaches is to save all values that reside in caller save registers to the stack prior to each function call. But that sounds expensive. That way, if the register allocator chooses to assign x to a caller saved register, its value will be preserved. Huh, right. Yeah. However, saving and restoring to the stack is relatively slow. If x is not used many times, it may be better to assign x to a stack location in the first place. Better yet, if we can arrange for x to be placed in a callee saved register, then it won't need to be saved and restored during function calls. What? So right. If x is not used many times, it may be better to assign it to that location in the first place. Right, so if we're gonna use it just a few times, we just push it on the stack instead of having to push and pop it from the stack constantly. I mean, moving it from a register to the stack and so on. I'm not sure I understand exactly this, so I'll just keep going. And hopefully at some point it will click. Da-da-da-da. Yeah, I think I'm gonna have to read this again tomorrow after a good night of sleep. So essentially, this is saying that we would grab a particular function, right, or a particular program, and traverse it backwards, right? And as we traverse it backwards, we will start with an empty. I think, yeah, we would start with an empty set, right, of, well, it's called a live, sort of live before, live after set. That's the name it's given here, but it's essentially a set of locations, right? Like things that are currently being used for this particular instruction. So, for example, here in the conclusion, I guess here, right? If we go backwards, we start from zero, right? And eventually we end up with RSP and RBP. These are two locations that we're definitely using, right? So that will be our set, I think, if I'm reading this right. And then, of course, if you keep going upwards, then you'll see like, oh, we're actually using these auto registers or these stack locations and stuff like that. And you will start growing that set of things. Or rather, instruction per instruction, you will have a different set of locations. Now, I'm not entirely sure what it's going to be doing with those sets of locations, right? But I know that they change from instruction to instruction, so they may shrink, right, as you go upwards, or they may get bigger, right, depending on whether the variables are still alive, I guess, or being used. There's a couple of exercises here, which is, it's great, but also kind of sucks. Like, I'd sit down and actually think through this stuff and try to figure out, like, oh, this is how it works. Which is great because it forces me to think, but also it's like, I wish I could just, like, read through the thing, right? So if it makes sense, I'll understand it, and then I can move on. Else, I can keep digging or get all the material. But here is like, oh, you know, do the liveness analysis by hand on this thing, right? And compare the solutions and stuff like that. Instead of showing me how to do it by hand, I have to. Anyways, build a graph, interference graph. Okay, thankfully we have Okama libraries for that as well. Ooh, and then we go into graph coloring via Sudoku. We come to the main event discussed in this chapter, mapping variables, registers, and stack locations. Variables that interfere with each other must be mapped to different locations. In terms of the interference graph, this means that adjacent vertices must be mapped to different locations. If we think of locations as colors, the register allocation problem becomes a graph coloring problem. Balakrishnan, 1996, Rosen, 2002. The reader may be more familiar with the graph coloring problem that he or she realizes. The popular game of Sudoku is an instance of the graph coloring problem. I didn't know that. Following describes how to build a graph out of an initial Sudoku board. There is one vertex on the graph for each Sudoku square. Okay. Okay. There's an edge between two vertices if the corresponding squares are in the same row, in the same column, or in the same 3 by 3 region. Now choose 9 colors to correspond to the numbers 1 to 9. On the basis of the initial assignment of numbers to squares on the Sudoku board, assign the corresponding colors to the corresponding vertices in the graph. Okay. If you can color the remaining vertices in the graph with the 9 colors, then you have also solved the corresponding game of Sudoku. Yeah, that makes sense. Cool. Cool. All right. Next chapter goes into booleans and conditionals. I'll definitely reread chapter 3 tomorrow and start implementing some of that. I think I have a rough idea of how to get started. We'll see how far we go. Chapter after that goes into booleans and conditionals. It introduced the type, which we didn't have so far, right? And, conditionals and all the boolean operations like not, and or. Right, so this actually starts the type checking as well. Ooh, exciting. Yeah, and we have a type checker as well. Officially tired, so we'll be wrapping up in just a moment. Just quickly scanning through the chapter 4, seeing the kind of changes we'll have to make to the different passes. Cool. All right. I think that's it for today. Thanks so much for watching, everyone. Happy that we got to fix a couple of bugs. We got the program running again. The debugger on VS Code is working, which is excellent. I reckon that probably we can call LLDB as well. Yeah. So I don't know if I'll stream tomorrow, but if I do, we'll be working on register allocation. And if that works fine, I expect I'll need to read up on graph coloring algorithms again. Yikes. It's been a while. But yeah. All right. Take care, folks. Good night.